Good morning. This is lecture 30, module 5. We are continuing with matrix analysis of beams and grids. So we will complete the reduced stiffness method which we started in the last class for the beam element, and in the next class we will take up flexibility method for the beam element, and after that we will do again reduced stiffness method for the grid element and the conventional stiffness methods. This is covered in the chapter on beams and grids in the book on advanced structural analysis. Of the three methods, we are now looking at reduced element stiffness method. If you recall, we learned how to derive the stiffness matrix using various techniques. The easiest is a physical approach. That matrix is very easy to remember: 4EI by L, 2EI by L, 4EI by L, 2EI by L. The diagonal elements are 4EI by L, the off diagonal elements are 2EI by L. They are all positive, and you physically know the meaning of each coefficient in that matrix. We also learned how to set up the TD matrix, and the real problem is when you have to convert deflections in the main structure in the beam to a reduced element stiffness coordinate system at the local level, and we said this can be done by converting the chord rotations to equivalent flexural end rotations. So if you have a chord rotation of 1 by L corresponding to unit displacement, you can treat that as an equivalent end rotation, but remember you have to reverse the sign. That means if you have a clockwise chord rotation, you should have an equivalent anti-clockwise chord rotation. This is how you convert from typical global coordinates like M, L, M, N, P to the two coordinates 1 star, 2 star. We have done this in the last class, but if you found this little difficult, there is an alternative way of arriving at the same derivation. How do you do that? No, not T into it. You have to bring in the transpose. You have to invoke the contra gradient principle, and some of you might find it easier to do it this way. So here we do the reverse. We move from the local coordinates to the global coordinates, and we invoke the TDI transpose matrix, which means you apply a unit moment, end moment, two of them, one at a time, like this. You apply F1 star equal to 1, satisfy equilibrium, and figure out what are the corresponding values that you get in the global coordinate systems. Next you apply F2 star equal to 1, and you can see that of the two end moments only one is non-zero, and it has a value of +1, and you get two reactions. You can see very clearly it is 1 by L. If it is pointing upward, it is positive. If it is pointing downward, it is negative, and you can very easily generate this matrix. You get it? So this is another powerful way of generating the same transformation matrix, but we are getting it from the transpose. Okay. But my suggestion is do it the classical way, the TD approach, using the displacement transformation. Now if you recall, we did this problem in the last class, and we will now look at more problems. We will try to do 3 quick problems in this session. With that we will close the reduced element stiffness method. We need to worry about how to deal with moment releases. There are 2 kinds of moment releases that you can get. One is when the far end is a hinged or roller support. The second is you have an internal hinge. Either way, the bending moment in the beam at that hinge location is known. Usually it is 0 unless you have an externally applied known value of a concentrated moment. So we have done this, we have taken advantage in terms of reduced kinematic indeterminacy when we applied the slope deflection method and moment distribution method, remember. So we can do the same thing, that means we need to, here we just ignore that global degree of freedom altogether, we do not even give it a number. If you have a hinge, whether an external hinge or an internal hinge, do not assign a global coordinate, active or restrained at all, just skip it. We will see how to do that, and modify the element stiffness matrix. You know that 4 EI by L will now become 3 EI by L when the far end is hinged, so that advantage will take care of. And you also need to modify the fixed end forces, because normally you have the formulas for a cantilever which is fixed, beam which is fixed. If one of the ends has a moment release, it becomes a propped cantilever and you know what to do. Okay, we have studied that. And the big change that you get is, in the conventional stiffness method, how many degrees of freedom did you have? 4. You dealt with a 4 by 4 element stiffness matrix. That reduced to 2 when we did the reduced element stiffness method, where we did not take any shortcuts. That will now further reduce to 1. That will now further reduce to 1. Remember we had 4 EI by L and 2 EI by L, and then we had this 2 by 2 matrix. Now we do not worry about rotations at the other end, at the hinged end, and so you have only a 1 by 1 matrix, just one coordinate, the other end is hinged. So that is a major advantage we are trying to take in this method. You reduce the degree of kinematic indeterminacy, and you know that the element stiffness matrix is 1 by 1 and the coefficient is 3 EI by L. Is it clear? We have done exactly this in slope deflection and moment distribution method when we took the simplification. So we will see how to do this. Let us take this problem. We have done this problem earlier? Yes, I think so. In matrix methods or in moment distribution slope deflection? One of them anyway. So how do you, or did we do it in the, I think we did the conventional stiffness method, remember. What was the degree of indeterminacy? We did this, yes. Not 3, it was 5. It was 5 because theta B was D1, theta C was D2, theta D was D3, then delta E, we did not take any shortcuts, was D4, and theta E was D5. Remember there were 5 active degrees of freedom and there were also 5 restrained degrees of freedom. We had a 10 by 10 structure stiffness matrix, the Ka was 5 by 5, remember that. Now we are going to have a massive reduction in kinematic indeterminacy. So what should we do first? Because this is aimed at manual analysis, so we do not want to solve 5 by 5 matrices. The first thing you can note is you have an overhang which you can just get rid of it, because that region is statically determinate. So that is the first thing you do. You separate it out and you bring it back at the end when you need to draw the bending moment and shear force diagrams. So when you remove it, you know that if you have a clockwise moment of 50 kilonewton meter at the free end E, you have an anti-clockwise moment at D, and Newton's third law says the same moment will act in the opposite direction in the segment ABCD at D. So you are now applying this as a nodal moment, except that it is not really going to a global coordinate. We will see, we will explain that shortly. Okay, now tell me, we have got a reduced problem now, just a 3 span continuous beam. What is the degree of kinematic indeterminacy in this? It is just 2 if you want to take advantage of the hinge at D, right. So from 5 it is a massive plunge to 2. So that is a clever thing and we should do it correctly without making any mistakes. So please pay attention. By the way, we did this in slope deflection method. We did this in moment distribution method. We will now do it in matrix method. So the first thing is, the procedure is quite clear. You have to do the coordinate transformation, write down your displacement transformation matrices. You have to figure out the fixed end force vector. You have to do this manually because you have a problem in the reduced element stiffness method, because you do not have a constant fixed end moment, it can change. So you have to do it manually. You have to get the net resultant force vector Fa by FFA. Then of course you generate the stiffness matrices in the usual way, and you solve the equilibrium equations, find the unknown displacements, use those active displacements to find the support reactions, and in the end you find the fixed end forces. And if you recall our previous discussion, that last equation, what does it really represent in terms of what we did earlier? They are nothing but slope deflection equations, right? Remember I said MAB is MFAB plus 4EI by, so all that is, it's a matrix formulation of slope deflection equations. Okay, so let's proceed. The first thing you need to do is find the coordinate transformation. Okay, so you've got global coordinates here. We agree that we'll have only 2 active degrees of freedom, 1 and 2. At the end D, what should you do? Leave it in peace. Don't put a curled arrow there and give it a number, because we are not interested in that rotation. We don't want to know theta D, because we know the bending moment at D is, in this case, 50 kilonewton meter. We will bring all that later, but the first step is, if you want to work with reduced kinematic indeterminacy, don't include that as an active degree of freedom. But you have restrained degrees of freedom, 3, 4, 5, 6, 7 in the usual convention. We will do that. Why are we putting the restrained degrees of freedom? Because we want to find support reactions, that is the real reason. Also, if you have, in this case we also have that, what do we have? We have support settlements in this problem. So you have to bring that into the picture, and let us look at that. We have 2 support settlements. Remember, B and C go down by 5 and 10 mm respectively. So you will label that as D5 equal to minus 0.005 meter and D6 as minus 0.010 meter. Next question, are there any nodal loads in this structure Fa? You will find that there were only distributed loads, and there was some concentrated load in the middle of that beam. You had a nodal moment at D, but it doesn't have a number. So how do you deal with that? You understand the moment at D. That becomes a load which you have to account for in the fixed end force vector for the element 3. Okay, that is the only catch. You have to do it carefully, and then you can solve the problem. And we did it in slope deflection moment distribution method. So let us see how to proceed. These are our element level local coordinates. We have 3 elements, and for each element we usually have 2 degrees of freedom, except for the third element. The third element has 1 degree of freedom. Please pay attention. Okay, 1 degree of freedom, and you have to be careful about that. Okay, so please write down the transformation matrix for what will be the size of that matrix. It is going to look like this, at least get it right. So for the first element, what is the size of the TD matrix? How many rows will there be? 2 rows for the first element. How many columns will there be? There will be 7, because there are 7 coordinates, of which 2 belong to TDA and 5 belong to TDR. Can you fill up that? Similarly, you will do it for the second element, and for the third element, and you can do it all in one go. For the third element, it was just 1 row. Okay, so give it a shot. Very easy. If you apply D1 equal to 1 in the main structure, what do you think will happen? Most of those numbers will be 0 except D2 star for element 1 and D1 star for element 2. That's it. So I've given the solution here. Let's go through it carefully. If I apply D1 equal to 1 here, you agree that the second element in the second, well, we have two elements here. One is the element in the matrix and you have the actual beam element. Okay. So when I say element, I am referring to the element in the matrix. The second element in the first beam element will be 1 and the first element in the second beam element will be 1 and the rest will be 0. Clear? Now you apply D2, that means this one, D2 equal to 1. You agree this will get affected and this will get affected, which will show up as 0 0 0 1 1. Clear? Next we apply D3 equal to 1, which means we are lifting up the left end A and restraining all the other coordinates. This will result in a clockwise chord rotation in the element 1 alone. Clockwise chord rotation of magnitude 1 by 8. 1 by 8 is 0.125. Okay, and it's if you have a clockwise chord rotation, you end up with equivalent anti-clockwise positive end rotations, and that's why you write plus 0.125 plus 0.125 for the first element and you write 0 0 0 for the other element, and so on and so forth. So I am sure you can derive for all the others. Let's look at the last one. Let's say D7 equal to 1. If you lift up the last one, only element 3 will be affected. Agreed? Only element 3 will be affected. You have a clockwise or anti-clockwise chord rotation? You have an anti-clockwise chord rotation, and the equivalent flexural rotation will be clockwise, which means negative, and it will be 1 divided by 6. That's why you have in the last row you have minus 0.1667, but all the others are 0. Is it clear? Can you all do this correctly without making any mistake? Do you have any doubts on this? This is the first step. If you get it right, you will get everything right. Speak louder. Global coordinate 4, yes. Global coordinate 4 is here, yes. You have a unit rotation, it will affect only beam element 1. Okay, you have to be careful when you read these rows. This is 1 0 0 0 0. Okay, it's my fault. I didn't align all the rows correctly, all the columns correctly. Is it clear? No mistake, everything is fine. We'll proceed. Now we have to find the fixed end forces. We've done this problem earlier, so can I go fast over this? You can work out the fixed end forces. Remember, you also need to find the vertical reactions. Why do we need to do that? Not only the fixed end moments, also the vertical reactions, because in the global coordinate they pile on to those vertical forces in the coordinates you've identified. So you need to do that little extra exercise, but that's easy to do. We've done that earlier. Take the second element, we've done this before. Remember, here the only thing to worry about is the formula when half the span is loaded with a UDL, for which you may have to look up a table because you may not remember it. Remember, it's 5 by 192 WL squared and 11 by 192. That's the only form, but we've done this earlier. What about the third one? Okay, the fourth element you don't worry because you've already dealt with it. In the third element you have to be careful because the ND is now roller, and you're going to apply a 50 kilonewton meter at that ND clockwise as a load. Please tell me what's the fixed end moment you get at C. Please calculate and tell me, because this is where you can go wrong. This value, that is F for the element 3 1 star. Calculate it and tell me. You have done this when you did slope deflection method moment. Do it once more. Well, due to the 150 kilonewton load, for a fixed beam, you know the formula, WA squared by L squared for the left end, and for the right end it is WA squared B by L squared, and you need to release that, so half of it gets carried over to this side, so that part you can deal with. What about that 50 kilonewton meter? Half of it gets carried over with the correct sign, so that's all you need to do. I hope you understood. Don't go wrong here, because we are taking shortcuts. Shortcuts can be taken only by intelligent people, otherwise you get lost in the woods. But the workload reduces enormously, right? We've reduced the indeterminate. Any doubts on this? We've done similar problems earlier. Okay, right. Keep the signs intact correctly. What do we do next? We write down the fixed end force vector. You can put it all in one box, or you can keep them separately as I have shown here. That is, these are only the end moments corresponding to the degrees of freedom. Typically 2 degrees of freedom per element, except for element number 3, where you have only 1 degree of freedom. From here manually you have to build up the fixed end forces that act on the main structure. Finally we want that, we want FFA and FFR. So we can get that. We need, so this is a fixed end force vector in the global coordinates. FFA correspond to the two coordinates 1 and 2. Remember 1 and 2. 1 and 2 are here, these two moments and these two moments, right? So you just algebraically add up those two moments, you will get F1F, F2F. Is this clear? The net moment that you get corresponding to the fixed end moments at B and C, that's F1F and F2F. And what is F3F, F4F? You can pick up from here. Remember this was F3F. So that is plus 120. F4F is plus 160. F5F is a summation of 120 kilonewton and 61.25, 181.25. F6F is likewise summation of these two, and F7F is 34.72. Is it clear? It's easy to do, but you have to do it with your eyes open manually. Okay, now let's proceed. Well, not really manually, you can also program it if you do it skillfully. So you can find the net load vector, which is the nodal force vector. In this case it's a null vector, there are no nodal forces in this problem, and FFA, which we got in the last step. You have to put a minus sign because you have to satisfy equilibrium, and you will find that you are actually getting, you have reduced that complicated problem to a simple problem where you apply only 2 nodal moments in the direction shown, and this is equivalent to the original problem in the sense you get exactly the same theta B and theta C, and that is the beauty of the displacement method. Such a complicated problem you have reduced to a simple problem where you have only nodal forces. Next, generate the element and structure stiffness matrices. This is easy, remember 4EI by L, 2EI by L. So this is, put the right EI, in this case EI is 4EI in this problem, L is 8, so they are easy to write. Next element 3EI and L is 6. So you see it's very easy. Please write down for the third element, because third element is different. Yeah, there is only one, it is a 1 by 1 matrix. The EI here is 2 EI and the L is 6, but you have to, it is 3 EI by L. Is it clear? EI into 1. It is easy. Now can you assemble? Yes. Well, you first do this product, we have done this before, let us not waste time. You have got the TD matrix in the beginning, you understood how to do it, just pre-multiply that with the Ki star matrix, get this, then what do you do again, pre-multiply this with TD transpose, and then just add up everything, add up mechanically, no slotting required here. That is the beauty of this TD, not just reduce, when you use TD even in the conventional you get this advantage, and the top upper corner on the left side is your KAA, and that is your real You don't worry about the size of the whole matrix. It's 7 by 7, it looks scary. But we want to only invert 2 by 2, that's Ka, you can pick it out, and inverting it is easy, and you are ready to take any load. But the loads are also known, these equations are well known. It is always good to find out Ka, dA directly. In this case you have support settlements, so dr is given as, we did this earlier, minus 0.005 meter, minus 0.010 meter at 5 and 6 coordinates, but EI is 80,000. You have an option either to plug in 80,000 in the stiffness matrix, or you try to get rid of EI by converting these deflections in millimeters to equivalent EI terms. You understand? In other words, if you multiply these two with 80,000, you can write this as 1 by EI into minus 400 minus 800. In short, if you take this product, you will get minus 0.005 meter. Is it clear? This is a clever trick to do so that you leave your stiffness matrix in peace, that EI gets cancelled out. And there are 5 elements here because there are 5 restraint coordinates. You know that there is no rotational slip or settlement anywhere else, so it is 0 0 minus 400 minus 800 0. Is it clear? Now you are all set to apply and solve. You first take care of the dr kr. You can do this stepwise or you can do it in one shot, I leave it to you. Finally you get the answer, okay, you get the unknown displacements, and we have solved this problem earlier by the hard conventional stiffness method. You get, if you check up, you get exactly the same solutions. Now you need the support reactions. This is where you have to look at the big KRA and KRR matrices which you generated in your stiffness, but we have done this in the conventional stiffness method. So this step is same to that, similar, there is no difference. So you should get exactly the same answers because only dA was unknown here, the rest we had derived earlier in the conventional stiffness method, and you will find you are getting the same reactions. Last step, member end forces. So remember those slope deflection equations. So you know all the displacements, both the active and the restraint, and for the first element plug in those values, second element, third element, you get the same answers as we did earlier, and finally you have to draw the same bending moment and shear force diagram. Is this clear? It is a powerful shortcut method. Instead of solving for 5 unknown displacements, we solved for only 2. Our interest was to get the final solution, to design this beam, so we need to know the bending moment diagram and shear force diagram, and we have got it. We will do the same problem tomorrow using the flexibility method, and you can decide which is the easiest to do. Okay, we have not done this in moment distribution or slope deflection method. How to deal with an internal hinge in the reduced element stiffness formulation. You will find that it is easier to do this here than in the conventional stiffness method, because there you have to artificially create a clamp and all that. Here life is easy, this is all you need to do. First of all, whenever you see a hinge, avoid putting any global coordinate there, active or restrained, because we want to take a shortcut. So remember earlier we had a coordinate 2 here and we had a clamp there, now we just leave it in peace. There is a hinge there, so that is what you have to note. There is no coordinate corresponding to rotation at B because there is no unique value for rotation there. Both the ends can move and you do not care with how much they move, because you just want the bending moment and shear force diagram. You are not looking for the absolute value of the rotations there, that is the real idea. Okay, ideally we should show a hinge also at B to remind us. Okay, the other coordinates are clear. 2, so the coordinate 2 now shifts here, 2, 3, 4, 5. So 1 active degree of freedom, 4 restraint degrees of freedom, same methodology. This is beautiful because you have only 1 degree of freedom for each of the 2 elements, and the stiffness is 3I by L. Can you write down the TD matrix for this? It is very easy, 1 row for each. Fill up this matrix. So it is going to look like this. Let us check it out. If I lift up B by unity and do not allow any other movements, then I have an anti-clockwise chord rotation 1 by 10 for this element, which will give me, should it be minus or plus? Minus, because anti-clockwise chord rotation is clockwise equivalent flexural rotation, so it is minus, and for this I get plus because it is the opposite. So that is how I fill up the first column. Is it clear? Second column, how do I fill up? Second column is simple. I lift up this. If I lift up this, I have a clockwise chord rotation for this and nothing for the second one, so I get anti-clockwise positive 0.10. Third one, this will give me 1 here and 0 here and so on and so forth. Very clear, simple, easy to do once you get the hang of it, right? Okay, we will move ahead. Fixed end forces. Here remember there was a nodal moment 30 kilonewton meter to the left of the hinge. So you have to find out the fixed end forces, and we have done this before. Is this clear? Due to this 100 kilonewton load, you get a fixed end moment here, which is WL by 8 into 1.5 times because of the propped cantilever effect. I hope you remember that, and it is anti-clockwise, so it is positive, but you have a clockwise end moment here of 30 kilonewton meter given as a load in the problem, but you are taking it at the element level, and so half of it gets carried over with the same sign, and it is clockwise, so you should put a minus sign here. Is it clear? Once you calculate this, it is easy to calculate your vertical reactions. Okay, there is a reaction here, there is an arrow that should be here, you get the reactions. We did this earlier also. Similarly, you do it for the next beam. Okay, there is a hinge, but there is no nodal moment at B. This is a straightforward problem. WL squared by 12 into 1.5, 3 by 2. Find the vertical reactions. Now, can you assemble the fixed end force vector? Well, yes. Can you find out FFA and FFR? Well, it is easy. Do it by inspection. Corresponding to this coordinate 1, you have to add up this reaction and this reaction, right? It adds up to 73.25, and similarly you can fill all the other fixed end coordinates, 1 active and 4 restrained. Is this clear? Actually the procedure is similar to the earlier procedure, so we do not have time to actually sit and write down all the numbers, but that is something you need to do when you go back home and refresh your understanding, prepare for the exam. But the procedure, is it clear? Sorry? We got fixed end moments at the element level, yes. You are going back to, you can't do that in reduced element stiffness method. Got it? You are right, you can normally do it, and you should do it in conventional stiffness method, but do not ever think of doing it in reduced element stiffness method, because reduced element stiffness method has reduced coordinates, it can't handle this complexity. You have to do it manually, so you have to look through inspection, do it. Is it clear? Please remember this, because a common mistake people might make, you can't do it here. Okay, so you have an equivalent joint load, and this is what we have to analyze, and that is easy. Let us generate the element stiffness matrices. You have 2 elements, single degree of freedom, EI, 3 EI by L, easy to do, you got those numbers. Then you know the TD matrices, so TD, K star TD you can work out, and then do the summation. You will get 2 contributions. The first contribution comes from the first element, second contribution comes from the second element, and you just add up, you will get the final stiffness matrix. K is 1 by 1, very easy to do. You can find the inverse, which is just a reciprocal. Same formulas, these are now looking very, very familiar, there is nothing great in all this. Solve for the unknown, single unknown displacement D1 in the middle, Remember we did this problem, we got 101 mm in the conventional stiffness method. We also noted that when the hinge was not there, the deflection was very small. The hinge made the whole system very flexible. The deflection shot up by a large amount. Find out the support reactions, they match with what you solved earlier using the clamp, but this is much easier. One unknown here, and there you had to bring in the clamp. So next, member forces, same procedure, same member end forces, same shear force diagram, same bending moment. Is it clear? So we are really doing the same problems by all the methods so that you get a clear idea, and it's an easy check, and the check is even better when we do by flexibility method, which is a completely different approach, and you are getting exactly the same solution. Okay. Last problem, and this has to do with guided fixed supports, and this is a little it requires a little understanding, and please listen carefully. So here you have what can be called a shear release. It's not a moment release, because in a guided fixed support there is no shear transfer from the beam to the support, okay. And like in the previous case, you ignore the degree of freedom associated with the member end release, that means the translation you ignore. We did this in moment distribution method, slope deflection method, do the same thing. Modify the element stiffness. What will be the element stiffness for a guided fixed support case?
Yeah.
Remember those three magic numbers, your 4 EI by L, 3 EI by L, yeah. Which one will you use?
EI by L.
So that's all, only one number to remember, you remember it very well. You can prove it, it's a cantilever behavior, and that's the element that you can assume. This is here we will take Ramesh's suggestion. Remember in the beginning he said, why do you always take a simply supported beam as the element, why can't you take a cantilever? Here it's ideal to take a cantilever because the behavior is exactly like a cantilever. So my suggestion is, you can take this element, but it looks so complicated, right? Why don't we take a much simpler element, and that simpler element is this simple cantilever fixed at the other end, and you remember, you know that the stiffness is the same. There are two ways of getting EI by L. So we will use this in our symbols so that our understanding is simplified. Is it clear? Okay, so let's demonstrate this with this same example which we did earlier. So we can take advantage of the symmetry, cut it into two, and you get a guided fixed support there. What's the degree of indeterminacy here? Kinematic indeterminacy. 2 normally. Which 2? Don't say AB, tell me theta, delta, which one? Theta A, theta B.
Theta B and delta C.
Well, strictly speaking, theta A, theta B, delta C. But the whole idea of demonstrating this is to take advantage of. So there are two advantages you can take. One is delta C, you don't worry about. The other is theta A, also you don't worry about. What was the previous example? Far end is hinge. So you guys should wake up. Whenever you get a nice shortcut, take it. From 3 we have reduced to 1 single unknown. What's that single unknown? Theta B. Do you want to do a 3 by 3 matrix inversion or 1 by 1 matrix? 1 by 1. So be intelligent, do one, the procedure is the same. Okay, take a look here. This is the reduced beam problem. These are the global coordinates, just one, is it okay? Just one, and 2, 3 and 4 are restrained in the global coordinates. Local coordinates, just one but simply supported I have shown here, and cantilever I have shown here, is it okay? 1 star, 1 star, you know the stiffnesses. For the left one it is 3 EI by L, for the right one it is EI by L, that is it. Write down the TD matrix. Write down the TD matrix. What will be the size of the TD matrix for each of those elements? 1 by 4. So you have to give me 8 numbers. And we are covering all types of problems, all types of complexities, all types of shortcuts. Okay, so let's check it out. If you lift up, if you put this rotation 1, it will affect this and this, right? So you get 1 1 both anti-clockwise positive. If you put d2 equal to 1, that means you lift up this end, which is simply supported, you get a clockwise rotation in element 1, right, which means anti-clockwise equivalent flexural rotation. 1 by 4 is how much? 0.5 plus 0.25, but nothing happens to the second element, so this is 0. If you lift up the middle here 3, left will undergo anti-clockwise chord rotation of 1 divided by 4, which means minus, because it is a clockwise equivalent end moment, 0.25, whereas nothing, and for the right end, now you have to be careful. Now you have to be careful. In a cantilever, translations don't create any problem. In a cantilever, remember it was guided fix here and support here. If you have support settlements, it's not going to create any problems. You have to visualize it. So this is where you don't make mistakes. Okay, your TD value will be 0 because this is a different ball game, right? Because B is meant to deflect. B is free. Nobody is stopping that deflection. Let it deflect. It's a rigid body movement. The whole thing will go up. So you have to be careful. This is where you recited from memory. It didn't work here. You have to always use your brain. That's the only thing. The last one is it clear? Item number 4, anti-clockwise moment. Here you have to be careful. If you give an anti-clockwise here, at the other end you will have an equivalent clockwise opposite moment. So this is the only thing you have to be careful about. Maybe you might like it in the old style. Okay, let's try to generate the TD matrix for this guided fixed support case from first principles. So you have guided fixed support here, prop here, and we first take the case where you have a movement here. If you have a movement here, it will just move like that, okay, just move like that, a rigid body movement. So in terms of rotations, you don't have any rotations, so that's why the rotation value is 0. In the second case, we are dealing with a rotation, an anti-clockwise rotation at the right end, which means this rotation is now unity, and we need to draw the deflected shape and figure out what is the rotation at the left end. We will take the same boundary conditions. And you must recognize that there is a possibility for the beam to deflect at this end because you have a guided roller support here. So this is a little tricky because you might be tempted to draw it like this. In which case this angle will be half this angle, which is not necessarily true because this can deflect. So let us take some help from the contra gradient principle and let us see what happens if in a beam element to satisfy equilibrium you have a moment, a unit moment acting here. To satisfy equilibrium you also need an equal and opposite moment acting here, 1. So the TD value should be -1, and the minus is quite clear because you have an anticlockwise rotation here, you have a clockwise rotation here, so it's certainly minus, but it's not -1/2, it's -1, which means this has to deflect some more, and that's not a problem. So let's say this goes down to a point there, you can get the desired deflection. Still maintaining this change in angle is 1 here, and from half this increases to 1. So that's a physical explanation, and the answer is absolutely crystal clear, it has to be -1. Okay, so there are two explanations why you need to put -1 when you are dealing with this case, and you have to put 0 when you are dealing with this case, because there is no rotation happening in this case. Fixed end forces, can you find out? Okay, let's look at fixed end forces. Fixed end forces for the first one is 30 kilonewton meter, and for the second one we've done this problem earlier, right? You get 5 kilonewton meter, you can add up and get the resultant force vector, which is 5 kilonewton meter, and you have this matrix 5 kilonewton meter, and substitute your, is this clear? You get 3 EI by L for the first element, EI by L for the second element, and plug in those values, you will get the stiffness matrix, okay, and find the inverse. Same procedure, find the unknown displacement, it's -4 EI, 4 by EI, find the support reaction, you will get exactly what we got earlier. Member forces, that's it. So be careful about this particular shortcut, but you can cross check with your previous examples. When you have doubts about TD, check with TD transpose, because you are very comfortable with equilibrium, right? Be careful. So, but we have covered all the possibilities that you can get. So we have now reached a stage where we have finished conventional stiffness method, we did 4 examples, we have finished reduced element stiffness method, we did the same 4 examples. Now what is left is flexibility method, we will do only 2 examples, we will finish it tomorrow. And the last topic left is very interesting topic, grids. We are going into spatial structures, we will take some examples and do it. You have an assignment to do 3 problems, one of them is a grid. Okay, thank you.